The time illusion. Researchers studying quantum entanglement made a startling realization about the fundamental nature of time itself. The work suggested that what we experience as the passage of time might not be a basic property of the universe at all, but rather an emergent phenomenon arising from quantum correlations between particles. The breakthrough came when physicists applied mathematical frameworks to two entangled quantum states and discovered something extraordinary. Instead of time being a fundamental backdrop against which events unfold, their equations revealed that temporal progression could be described entirely in terms of quantum entanglement relationships. The system they studied could be perfectly described by standard quantum mechanics, yet time itself disappeared from the fundamental equations. What replaced it was even more remarkable. The apparent flow of time emerged from the quantum correlations between particles, with the states of tiny quantum systems acting as natural clocks. Their mathematical analysis showed that the familiar equations of physics could be reproduced without assuming time exists independently, suggesting that our experience of temporal flow is actually a consequence of quantum entanglement manifesting on macroscopic scales. This discovery represents a profound challenge to our understanding of reality. If time is truly emergent from quantum entanglement, then the universe operates in ways that are fundamentally different from our intuitive understanding. The passage of time wouldn't be something that happens to objects in the universe, but rather something that arises from the quantum mechanical relationships between those objects themselves. The implications are staggering. Every physical process we observe, from the decay of radioactive atoms to the expansion of the universe itself, might be better understood as manifestations of quantum entanglement, rather than events unfolding in time. This suggests that the cosmic story we tell ourselves about the universe evolving from past to future might be missing the deeper quantum reality that underlies all temporal experience. If these mind-blowing discoveries about time are fascinating you, hit that subscribe button and turn on notifications so you never miss our next video. The negative clock. In laboratory experiments designed to measure the behavior of atoms in excited quantum states, researchers encountered something that defied every assumption about the direction of time. When they measured how long atoms remained in excited states after being struck by photons, they found that the duration was negative. This wasn't a measurement error or experimental artifact. The atoms were spending negative time in their excited states, meaning that if you constructed a quantum clock to measure these durations, the clock would move backward rather than forward. The photons appeared to exit the material before they had entered it, creating a temporal sequence that violated our basic understanding of cause and effect. The experimental setup required 3 years of development to achieve the precision necessary to observe these quantum temporal effects. The results showed that under specific conditions, the absorption and emission processes in atoms could occur in ways that created negative time intervals. This discovery revealed that at the quantum level, the familiar arrow of time that governs our everyday experience might not apply. What makes this finding particularly significant is its implications for causality itself. The observation of negative time suggests that the fundamental processes governing atomic behavior operate according to temporal rules that are completely different from our macroscopic experience. Events can precede their causes, effects can occur before their triggers, and the entire framework of sequential causality that underlies classical physics breaks down at the quantum scale. The researchers demonstrated that photons could seem to exit a material before entering it, revealing observational evidence of negative time that challenges our linear understanding of temporal sequence. This discovery represents a fundamental challenge to the assumption that time only moves forward, suggesting instead that temporal direction might be bidirectional or even multidimensional at the quantum level. The dying universe. The Dark Energy Spectroscopic Instrument created a three-dimensional map of the universe spanning nearly 15 million galaxies and stretching back over 10 billion years of cosmic history. What they found challenged everything cosmologists thought they understood about the fate of the universe. Dark energy, the mysterious force driving the accelerated expansion of the cosmos, appeared to be weakening over time. This force, which makes up approximately 70% of the universe's total energy content, wasn't the constant, unchanging pressure that scientists had assumed. Instead, it was evolving, becoming less influential as the universe aged. The implications of this discovery are profound. For decades, cosmologists had predicted that dark energy's constant pressure would doom the universe to expand forever, eventually separating every particle by unbridgeable distances in a cold, empty cosmos. But dark energy that evolves over time makes alternative futures possible, potentially allowing for scenarios where expansion slows, stops, or even reverses. The data came from analyzing light that had traveled for billions of years across space, carrying information about the universe's expansion rate at different epochs in cosmic history. By measuring how galaxies cluster into subtle patterns that reflect ancient sound waves from the early universe, researchers could reconstruct the expansion history with unprecedented precision. What they discovered was that the universe's expansion has not been uniform over time. The influence of dark energy has varied, suggesting that this fundamental force is not a fixed property of space itself, but rather something that changes as the cosmos evolves. This finding represents one of the most significant challenges to our understanding of cosmic evolution since the original discovery of dark energy itself. The discovery has forced cosmologists to reconsider basic assumptions about the universe's ultimate destiny. If dark energy continues to weaken, the fate of the cosmos could be dramatically different from current predictions. Instead of endless expansion and heat death, alternative scenarios become possible, including cycles of expansion and contraction that could fundamentally alter our understanding of cosmic time itself. Smash that like button if you're learning something incredible about the nature of time and reality. We've got plenty more coming. The paradox solution. Theoretical work focused on one of physics' most persistent puzzles, the paradox associated with time travel. For decades, scenarios like the grandfather paradox had seemed to prove that backward time travel was logically impossible. But new research revealed that quantum mechanics itself might provide built-in solutions to these temporal contradictions. The work focused on closed time-like curves, theoretical paths through space-time that loop back to their own past. Previous analysis had suggested that such paths would inevitably lead to logical paradoxes, making them physically impossible. But the new research showed that quantum mechanical principles would automatically prevent these contradictions from arising. The key insight involved the relationship between entropy, memory, and information in quantum systems traveling through time loops. Any system following a closed time-like curve would experience a reset in entropy during the journey, causing all processes, including memory formation, to reverse. This means that travelers through time loops would lose their memories of the journey, preventing them from creating paradox by interfering with their own past. The discovery revealed that memory formation is fundamentally tied to the increase of entropy over time, making it inherently unstable in systems that experience temporal reversal. As entropy decreases during the return portion of a time loop, all information storage processes reverse, ensuring that no observer can retain knowledge that would allow them to create causal contradictions. This finding suggests that the universe has built-in quantum mechanical safeguards that prevent temporal paradoxes. Rather than making time travel impossible, these mechanisms would allow it, while automatically preventing the logical contradictions that had seemed to rule it out. The implications extend beyond time travel to fundamental questions about the nature of causality, information, and consciousness itself. The millimeter effect. Using atomic clocks so accurate they could detect gravitational effects across distances smaller than the width of a pencil tip, researchers demonstrated time dilation at scales previously thought impossible to observe. Two atomic clocks separated by just 1 millimeter ticked at measurably different rates, proving that Einstein's theories operate even at the tiniest scales imaginable. This breakthrough required technological precision that pushed the boundaries of human measurement capability. The clocks could detect time differences that accumulated over periods as short as 30 minutes, with their accuracy improving by factors of 50 compared to any previous experiment. After 90 hours of continuous measurement, the precision achieved was so extraordinary that it opened entirely new realms of physics for exploration. The implications extend far beyond simple confirmation of relativity. These measurements revealed that the curvature of space-time affects quantum mechanical processes in ways that could bridge the gap between general relativity and quantum mechanics. The research suggested that measuring gravitational effects with even greater precision might reveal how gravity disrupts quantum coherence, potentially explaining why our macroscopic world appears classical rather than quantum. What makes this discovery particularly significant is its demonstration that Einstein's predictions hold true across scales from the cosmic to the subatomic. The same gravitational effects that bend light around massive stars and slow time near black holes operate with perfect consistency at distances measured in millimeters. This suggests a fundamental unity in the laws of physics that connects the largest and smallest scales of reality through the geometry of space-time itself. The measurements also revealed something unexpected about the nature of quantum systems in curved space-time. The atomic clocks weren't just measuring time dilation, they were experiencing it as quantum mechanical objects. Their quantum states were being influenced by gravitational fields in ways that provided new insights into how space, time, and quantum mechanics interact at the most fundamental level. The impossible black hole. Theoretical calculations prove that Kugelblitze, black holes formed entirely from concentrated light, cannot actually exist despite being mathematically allowed by general relativity. The research revealed that quantum effects would always prevent such formations from occurring. The key insight involved the Schwinger effect, a quantum phenomenon where intense electromagnetic fields spontaneously create matter and antimatter particles from empty space. When light becomes concentrated enough to theoretically form a black hole, the resulting electromagnetic fields would automatically trigger particle creation. These newly formed particles would carry away energy and prevent the light from achieving the density required for gravitational collapse. This discovery demonstrates fundamental limits to how energy can be concentrated in the universe. Even at the extreme densities required for black hole formation, quantum mechanical effects intervene to prevent certain types of gravitational collapse. The finding reveals deep connections between quantum field theory and general relativity that weren't previously understood. The implications extend to our understanding of the early universe, where such extreme energy concentrations might have existed. If Kugelblitze cannot form, then certain theoretical scenarios for primordial black hole formation must be reconsidered. The discovery also provides new insights into the fundamental relationship between electromagnetic fields and gravity at the quantum level. What makes this finding particularly remarkable is how it shows quantum mechanics actively preventing extreme gravitational effects. Rather than being overwhelmed by intense gravitational fields, quantum processes assert themselves precisely when such fields become most extreme. This suggests that the universe has built-in mechanisms that prevent certain types of gravitational pathology from occurring. The backward arrow. Research into quantum systems uncovered evidence that time can flow in two directions simultaneously at the fundamental level, challenging our most basic assumptions about temporal directionality and causality. The breakthrough came from analyzing mathematical equations that describe how quantum systems interact with their environments. Researchers discovered that these equations remained valid whether time moved forward or backward, suggesting that the directionality of time isn't built into the fundamental laws of quantum mechanics. Instead, temporal direction appeared to emerge from other factors. Most surprisingly, the equations contained a mathematical mechanism that preserved time symmetry even when standard simplifying assumptions were applied. This mechanism, called a time discontinuous factor, maintained the bidirectional nature of time at the quantum level while allowing for the emergence of apparent time direction in macroscopic systems. The discovery suggests that our experience of time flowing from past to future might be a macroscopic illusion that emerges from underlying quantum processes that are fundamentally symmetric in time. At the deepest level of reality, the distinction between past and future might not exist, with temporal direction being something that emerges only when quantum systems interact with their environments in specific ways. This finding has profound implications for our understanding of causality and the fundamental nature of physical processes. If time can flow in both directions at the quantum level, then the causal relationships we observe in the macroscopic world might be approximations that break down when examined at sufficient precision. The discovery opens new questions about the nature of memory, consciousness, and the experience of temporal flow itself. The quantum tornado. Researchers successfully created and observed supersolids, strange states of matter that combine the properties of solids and superfluids in ways that seem to violate common sense. These exotic quantum states exist nowhere naturally on Earth, but might be common in the most extreme environments in the universe. These supersolids exhibited quantum tornadoes when stirred, revealing internal structures that operated according to quantum mechanical principles despite being macroscopic objects. The achievement required cooling atoms to temperatures approaching absolute zero and manipulating them with magnetic fields of extraordinary precision. The resulting state of matter displayed properties that couldn't be explained by classical physics. The significance extends beyond laboratory curiosities. Astrophysicists suspect that supersolids might naturally occur inside neutron stars, where matter experiences pressures and magnetic fields far beyond anything achievable on Earth. Understanding these exotic states could provide insights into the behavior of matter under the most extreme conditions in the universe. The creation of supersolids also revealed new aspects of how quantum mechanics operates in macroscopic systems. The quantum tornadoes observed in these materials demonstrated that quantum coherence could persist across scales much larger than previously thought possible. This suggests that the boundary between quantum and classical behavior isn't as sharp as traditionally assumed. These discoveries in exotic matter states are revealing that the universe contains forms of matter and energy that operate according to principles we're only beginning to understand. The ability to create and control such states in laboratory settings provides new tools for exploring the fundamental nature of quantum mechanics and its applications to extreme astrophysical environments. The Cosmic Revision. Before we reveal the final discovery, make sure you're subscribed and have notifications turned on so you don't miss any of our mind-bending videos. The James Webb Space Telescope provided measurements of unprecedented precision that resolved long-standing conflicts about the rate of cosmic expansion. The new data suggested that previous tensions between different measurement methods might finally be resolved. The breakthrough came from using the telescope's extraordinary sensitivity to observe distant galaxies and measure their properties with accuracy impossible from ground-based observations. These measurements allowed astronomers to trace the expansion history of the universe with detail that revealed subtle changes in the expansion rate over billions of years of cosmic evolution. What the data showed was that the universe's expansion hasn't been as uniform as previously thought. Variations in the expansion rate at different epochs suggested that the forces driving cosmic evolution have changed over time in ways that weren't accounted for in standard cosmological models. The discovery provided new insights into the nature of dark energy and its role in shaping cosmic destiny. The implications for our understanding of cosmic time are profound. If the expansion rate has varied more than expected, then our calculations of the universe's age and the timing of major cosmic events might need significant revision. The discovery suggests that cosmic time itself might be more complex than the simple, uniform progression assumed in most cosmological models. These measurements also revealed new details about how structure formed in the early universe and how gravitational effects have influenced cosmic evolution over billions of years. The precision achieved by the James Webb Space Telescope has opened new windows into cosmic history that are revealing the universe to be more dynamic and complex than previously imagined. The Unified Theory. Researchers developed a mathematical object called the Elena tensor that appears to bridge the gap between quantum mechanics, general relativity, and electromagnetism in ways that could lead to a unified theory of physics. This mathematical framework addresses one of the deepest problems in modern physics: the apparent incompatibility between the curved spacetime of general relativity and the flat spacetime assumptions of quantum mechanics. The Elena tensor provides a way to transform curved spacetime descriptions into flat spacetime models while preserving all essential physical properties. The breakthrough revealed unexpected connections between seemingly separate aspects of physics. The tensor showed that charged particles naturally possess spin properties that align with quantum mechanical predictions, while simultaneously satisfying relativistic constraints. This suggests that quantum mechanics and relativity might be more compatible than previously thought. Most significantly, the mathematical framework offers new perspectives on the fundamental nature of mass, energy, and magnetic moments. By unifying these concepts within a single mathematical structure, the Elena tensor provides a pathway toward the long-sought theory that could explain all fundamental forces within a single framework. The discovery represents progress toward answering some of the deepest questions in physics about the nature of space, time, matter, and energy. If successful, this unified approach could revolutionize our understanding of everything from subatomic particles to cosmic evolution, providing a complete description of reality that encompasses all known physical phenomena. These 10 discoveries collectively represent a transformation in human understanding that rivals the great scientific revolutions of the past. From quantum laboratories to cosmic observatories, from atomic clocks to mathematical theories that redefine reality itself, each breakthrough has systematically dismantled the comfortable assumptions that have guided human thought for millennia. The universe we thought we inhabited, with its orderly progression from past to future, its predictable cause and effect relationships, and its separation between observer and observed, has been revealed as something far more mysterious and interconnected than anyone dared imagine. These discoveries aren't just academic curiosities confined to research journals and university laboratories. They represent a fundamental shift in how we understand the nature of existence itself. Consider what these findings mean for our everyday experience. Every moment of consciousness, every memory of the past, every anticipation of the future, occurs within a framework that these discoveries suggest might be fundamentally illusory. The sense of temporal flow that seems so obviously real, so central to human experience, emerges from quantum processes that operate according to completely different rules than our intuitive understanding suggests. The revelation that time might be emergent from quantum entanglement changes everything about how we conceive of reality. If temporal progression arises from correlations between particles rather than being a fundamental property of the universe, then every process we observe, from chemical reactions to biological evolution, represents manifestations of quantum relationships rather than events unfolding in time. The universe has shown us its true face, and we are forever changed. If you want to dive even deeper into how governments have tried to manipulate time itself, check out our previous video, 10 Time Machines the Government Tried to Hide, where we reveal the secret projects that tried to harness these very discoveries. Click the link on your screen now. Until next time, when we find out how.